Welcome to the week 9 tutorial, and today's topic is going to be about the it's going to be about the conservation of the momentum. So you remember that the conservation of the energy in general is going to be happen when we're going to have known a specific path for the forces that doing the work. So we're going to see how everything is going to be done in the case of the conservation of momentum. So we start with this example is about a rod or a bar has a mass of 10 kilogram and is rotating on a smooth surface with a constant angular velocity of the omega 1 is equal to 3 radian per second. So just imagine that you have the pen is rotating around the center point. Okay, then suddenly it's going to be hitting from one of its end the peak P without any rebounding. Try to find what will be the new angular velocity just after the end is going to be connected to the peak at the point B. So what we have here is that we are going to consider that we have the conservation of the momentum, and the equation we're going to use is going to be that the hp1 is going to be equal to the hp2. And from there, the hp1 is going to be the Ig of this bar, which is 1 over 12 multiplied by the mass multiplied by the length square multiplied by the omega 1, plus we have the mass multiplied by the velocity of the point G multiplied by the R from G to P. So at the beginning, when the bar is rotating around the point G, that means that the velocity B is going to be velocity at the point G is going to be equal to 0. Then we can find the momentum conservation for the first state. In the second state, when it's going to be hit at the point P, and the things will be changed. It's going to rotate around the point P. This will be the new rotation point. And then I can find what will be the value for the HP2, which is going to be mainly about the IP multiplied by the omega 2, because rotating around the point P in that case. Or I can write it down as the same way, the IG omega 2 plus the mass multiplied by the velocity at the point G in the second state multiplied by the distance from the point G to the point P. So we'll see how we can do the solution for both ends to find the answer. And the answer given to us here to be that first sketch the free body diagram. Angular momentum is conserved above the z-axis, and thus we're going to find that the hp1 is equal to the hp2. And by solving, we'll find that the omega 2 is equal to 0.75 radian per second. So we start first with defining the situation. The bar undergoes a rotation about a fixed axis. And state 1 is going to be through its mass center immediately before its end is going to be connected to the big P. Then it's going to be in the state 2 rotating around the point P immediately after its end connects to the big P. So the free body diagram is what we have, but we're going to sketch once again. So the first state is just rotating around the point G. So we have the Ig omega 1. Then the momentum is going to be a force hitting the point P. Just immediately after that, we are going to have the rotation to be around the point P. Okay, so the moment in that case is going to be, also the momentum after this case is going to be rotating around the point P, which can either be IP omega 2, or it can be simply equal to the mass multiplied by the velocity G in the state number 2, and plus the Ig omega 2. Both scenarios will give us the same answer. Now we have the mass known and the omega 1 known. We don't know what the omega 2. So we start by using the equation that we learned from the lecture slides. So first, the principle of the angular impulse and the momentum may be applied. So the hg1 plus the sigma of the moment from time 1 to time 2 integration with the function of delta t is equal to hg2. The problem is difficult to find any values for the forces or the time 1 and the time 2. So again, to ignore that, and we go directly to the conservation of the angular momentum, where the hp1 is going to be equal to the hp2. So the law of conservation means that the momentum of rotating object does not change unless some type of the external torques is going to be applied. So we start first with the solution by calculating the value for the Ig. The Ig is 1 over 12 mass multiplied by the length square. Now, good, we know the mass is 10, the length is 2, so we can find the answer for this part. So state 1, where the bar is rotates about the point G. So the HP1 is equal to the IG omega 1 plus the mass multiplied by the velocity in state number 1 multiplied by the radius between G and P. When the bar is rotating around the point G, that's means the velocity of the point G is equal to 0. Now try to do it. Try to rotate the pen in your hand, and you will find that the center point of the rotation have no velocity. It's actually going to be a pinpoint. So the equation now can be written as following. Okay, so the second bond will be removed, and we will end up by having that the HP1 is equal to 1 over 12 multiplied by the mass multiplied by the length square multiplied by the omega 1. So we found the first state. In the second state, it's rotated about the point P. The IP is 1 over 3 mass multiplied by the length square and multiplied by the omega 2. Now, these two sides should be equal. We know the omega 1, we don't know what the omega 2, and we can solve it. Or we can continue finding the HP2 as around the point G. In that case, we're going to calculate the IG omega 2 plus the mass multiplied by the VG 2 multiplied by the RG to P. We know that in the case of the rotation around the point P here, the velocity we're going to have here is going to be equal to the omega multiplied by the R. Okay, the omega multiplied by that R. So we can simply substitute this V value by the omega 2 multiplied by the RGP, and we're going to get the answer to be a mass multiplied by the omega 2 multiplied by the RG slash P square. Okay, and so for that, we're going to get the same answer. Anyway, now just say that the HB1 is equal to HB2. So we're going to have 1 over 12 on one side, 1 over 3 on the other side. We can simplify that because the 1 over 12 is something like a quarter of the 1 over 3. Okay, so that's how we're going to come to things. The ml square will be simplified from both ends. The omega 1 is known. The omega 2 can be solved. So that's the steps we're going to take now. Okay, now I can simplify this one with that one. Okay, and we're going to get that here, and this will be something like 4 times. Okay, or 1 over 4 for here. So it to be 1 over 4, or you can write down 4 here. Both cases are going to be the same. And we will end up that the quarter of the omega 1 is going to be equal to omega 2. Okay, or the omega 2 is going to be equal to the 3 divided by 4, and this will make it as 0.75 radian per second square to the counterclockwise. Done. This question is done. And once again, we get to repeat that in the class and hope we are going to find some questions from you so we can solve that question with